So in this video we're going to go over how to use Excel to find a quadratic regression model. So this will be pretty similar to what we did when we found a linear regression model. So the idea is that in real life we get data. We aren't given a certain number of points. We're usually given data sets, and we need to come up with mathematical models for the data set. So here we have a data set that has as its inputs nitrogen fertilizer measured in milligrams per liter. So this is measuring the milligrams of nitrogen that are being added per liter of soil. So it's a measurement per unit volume. And then adding nitrogen to the soil is causing possibly a change in grass growth rate. So what we're measuring as our outputs are the blades of grass produced as a function of the amount of nitrogen added to the soil. So the first step is going to be to make a scatter plot of this data using nitrogen as the input and blades of grass as the output. And we're going to do this model using Excel. So I'm going to switch over to Excel. And I've already typed my data into Excel. And then this is going to work just like it did with the linear regression model. You highlight your two columns of data. You make sure that your input column is first and your output column is second, so that Excel correctly guesses what the inputs and outputs are. And then we go to insert, and we insert a scatter plot with no connect the dots, and we right click on any data point. Actually, we should do quick layout and choose a layout that has axis titles, and then get rid of the series because there's only one set of data. So we'll eliminate that, and let me make this just a bit larger. So if I right click on a data point, I can add a trend line. And if we did a linear trend line like we did in previous assignments and added the r squared value to the chart, what we'll see is that a linear model doesn't fit this data very well. This data has some curvature to it. My r squared score is 0.53. The closer the r squared value is to 1, the better the model fits the data. The closer the r squared score is to 0, the worse the model fits the data. So this is a case where with an r squared of 0.53, the model's fitting the data moderately well, but it's not a great model. But what we'll do is, instead of fitting that linear regression model to it, let's right click on a data point and fit a quadratic regression model. So we're going to go add trend line, and then a quadratic function is a polynomial of degree 2. So we select a polynomial model, and the order or degree we want it to be 2. That matches the largest exponent in our model. And then we'll add the equation and the r squared value to this chart. And what you notice when you look at that r squared value is that it's 0.9665 now, a lot closer to 1 than the linear model was. And then we'll take and clean things up a little bit. Let me insert a text box. Text box, and then I'm going to make my text box isn't playing nicely with me. Insert a text box. There we go. And let's get the font a little bit larger so that we can actually see it. And instead of y, our outputs are blades of grass. So I'm going to do blades of grass b as a function of n, and we'll replace x, which is our inputs, with n for nitrogen. And I'm going to go alt equal to convert everything into an equation, get rid of a little bit of the funky space. I'm going to get rid of these lines, I think, so that we aren't having to look at the lines in the chart area. So there's the equation, and then we'd want to give it a good axis title. So this is blades. Come on. blades of grass is my output, and my input is going to be nitrogen. Nitrogen in milligrams per liter. So we clean up the axes. So just like we did with linear models, we want the chart titles to make sense. So this is going to be blades of grass as a function of, we'll say soil nitrogen content, something like that. So clean it up and get a nice graph. The next step is to look at the key features of the graph, the intercepts, the vertex, and interpret the meaning of those things. So to do that, I'm going to shift back into PowerPoint, and in PowerPoint I've already recorded the quadratic model that Excel gave me. So if I shift back over into PowerPoint, what I can see is that I've got my model that I got out of Excel already typed into PowerPoint, and I actually graphed this model using GeoGebra, and we can see it's got some key features, right? It has a vertex. We'd like to find and interpret the vertex. It has a horizontal intercept right here. Remember, this is the nitrogen axis. This is the nitrogen axis. This is the blades of grass axis. So we'll want to find and interpret this intercept, the vertex. We have a vertical intercept on the blades of grass axis. We want to find and interpret that. And then I have an intercept over here where nitrogen is negative, but I can't put negative nitrogen into my soil. So I know that this intercept right here is a garbage intercept. So there's no need to find and interpret it because it is meaningless in the context of this particular model. So we'll start off by trying to find this intercept right here, which is the easiest intercept to find. So switching slides. To find this intercept, what we want to recognize is that the input for nitrogen is going to be 0 milligrams per liter here. So it's just a matter of taking the model and inputting 0 milligrams per liter of nitrogen into the model. And when you plug a 0 into the model, the constant term is always going to turn out to be the vertical intercept, which I've rounded here to the nearest tenth. So this says 0 milligrams per liter of nitrogen, and the output is 1.8 blades of grass. So the interpretation for this intercept would be that if we don't fertilize the soil, we expect the average output for blades of grass grown to be 1.8. So it tells us basically what the control in the experiment would be. What happens if we don't do anything? So next, to find the vertex, we use the fact that the input, usually it's x equals negative b over 2a, that the x location of the vertex is the negative b over 2a from the quadratic formula. But because I have a contextual model, I don't have an x, I have n for nitrogen. So my nitrogen coordinate is going to be n equals negative b over 2a. So I know that b is the coefficient on the linear term and a is the coefficient on the squared term. So I just take these two numbers, a and b, and I plug them into the relationship. And this one actually simplified surprisingly nicely to 304.5. And then that gives you the input, the n value that generates the vertex. And now we just need the output in blades of grass. So we just plug negative b over 2a into the model for n. So b of 304.5, we plug it in, pop it into a calculator, and I get an approximation for it. I rounded to the nearest tenth. So the interpretation here is that if I fertilize with 304.5 milligrams per liter of nitrogen, the model is projecting that I get 29.6 blades of grass grown. And in terms of this contextual model, this would be the maximum grass blades grown that the model's projecting, right? It's projecting that the best we can do is 29.6 grass blades if we do 304.5 milligrams per liter. In a practical setting, this would mean that this fertilizer level would be the optimal amount of fertilizer because it's producing a maximum output. You can see as we continue up the input axis, the quadratic model is suggesting that we'll get decreasing returns on adding additional fertilizer. And indeed, in real life, you can over-fertilize and actually kill plants. So that interprets the vertex. Now you move and you need to get this intercept over here. And what we want to recognize is that this intercept is 0 blades of grass. The output is a 0 because we're at the 0 location on the vertical axis. So to get this intercept here, you set the equation equal to 0. You set B blades of grass equal to 0. So it goes into the output position. And then we need to solve for n, which I solved for by completing the square. I went through the completing the square process, and I got an approximation from the completing the square process of 618.8 as my input. So what this means in the terms in what this means in the context of the model is that if I fertilize at a level of 618.8 milligrams per liter, the model is suggesting I'm going to kill the grass. I get no blades of grass grown. So that would be how I would interpret that. That intercept is that it's the worst case of over-fertilization that I can possibly do. I've killed the plant by doing it. And of course, we wouldn't want to ever get over here. We'd want to find, hey, what's the optimal amount of fertilizer? And the vertex is telling us the optimal amount of fertilizer to use. And the last thing I could do is I could say, hey, let's take these intercepts that I found and identify from them a domain and range for the model, a contextual domain and range. So the domain is all about what can my nitrogen be, and I can see that for my model, the first thing that makes sense is 0 milligrams per liter of nitrogen, and I kill the plant at 618.8 milligrams per liter of oxygen. Down here where the graph is negative, it's suggesting that I get negative grass blades, and I can't grow negative grass blades. So I'm going to constrain my domain as letting nitrogen run from 0 to 618.8. And if I do that, my outputs, I see the worst case output I get is 0 blades of grass, and the best output my model gives me is 29.6. So as I let n run over the domain, I get a range for blades of grass that runs from 0 to 29.6.